equation. Okay, let's see. This is my YouTube channel, Physics and Universe. We share videos, we upload videos of our research topic on quantum mechanics and general relativity and tough integration, differentiation, and maths problem. See here what the question is telling. If you can ask any question or you can have any problem, you will share to me. And if you have any suggestion or you pick my error, then tell me in comment. I'm glad to hear it. Now see here. Tonight in this live, I will explain, or simply I'm telling you, I will solve a question based upon Schrödinger equation. Okay, means Schrödinger equation. First of all, oh, the dogs are barking. How many people? 0. See, first of all, listen. A brief discussion about Schrödinger equation. What is Schrödinger equation? Schrödinger equation is a very important, you can say that it's the backbone of quantum mechanics, in which it explains about a particle like electron, protons, atoms with the property of wave concept, and that wave concept is different than classical wave concept. There, in that wave concept, we think electron and other subatomic particles are quantum wave, matter wave. We call them matter wave. And Schrödinger explained all these waves with a wave equation that is called Schrödinger wave equation. It's different than classical wave, but while to understand the quantum Schrödinger equation, you will get some hint from the classical wave equation. So let's see what I'm going to do this. This is a matter wave function representing a particle. This is the matter wave function representing a particle.
Someone is telling you hi, Krishna 18.
Yes, hi, definitely hi. How are you? How are you? See, this is a problem based over Schrödinger equation, where Schrödinger equation is very useful in quantum mechanics. You can say that it's backbone of quantum mechanics, because while Schrödinger equation explained subatomic particle in terms of wave, but see here, that's not classical wave, not a string-like wave. It's a wave which is called matter wave. It's way different than classical wave, but it has some similarities also. If you try to understand matter wave very well, you have to understand classical wave also. And there is a research over this, that's my own research work. I believe that the matter wave has some similarity with classical wave. That's another topic. Here I'm going to show you this matter wave function. This is representing a free particle confined in a region. A region, see here, this function has some value. This is the value of this function when the particle is from minus a by 2 plus a by 2. Clear? But this function has 0 value when it is beyond this and this. I'm showing you this in a very simple diagram.
What is this emoji? Someone has Navghan C40. They send an emoji.
Okay, definitely emoji.
Lot of emojis. Okay.
That's all. Thanks for watching. And if you have any question related to Schrödinger equation or quantum mechanics, you can ask me. Or if you have any suggestion, you can share to me. See this. See. It's like here x is 0, Here x is equals to plus a by 2.
It's not mathematics. The person you are commenting on this live, Navran C40, it is quantum.
This is a mathematical calculation of quantum mechanics, Schrödinger equation.
If you are not familiar with Schrödinger equation and quantum mechanics, then you will not understand it. And if you want to view it, then you can view it. Okay? And keep the comments respectful.
Don't say that. See,
Analyze.
this is Schrödinger equation. We use Schrödinger equation in quantum mechanics. It's not mathematics, but it has a lot of mathematics in it. You can enjoy it. If you will enjoy mathematics, then you can enjoy this also. It's not mathematics, it's physics, but it has a lot of mathematics here. We do entirely this calculation over the mathematical equation, differentiation, integration, differentiation. See, this is a box within which there's a free particle in it, and here this function represents a subatomic particle inside this region only. See, from here to here, the particle can exist only from here to here, not to this. If x will be greater than minus a, smaller than minus a by 2, means if in this region there is no probability of the particle. To this region there is not even any probability of the particle. So keep in your mind that particle is always within this region. It will never go beyond this, Inside this is the equation of the particle. And this equation tells us that the matter wave for the particle has two components. One is the amplitude component and as a time component, which means it behaves as phase of the matter wave, and this behaves as the component. And see, one thing in quantum mechanics, while using Schrödinger equation in quantum mechanics, you can't plot this time function because it's imaginary. It's only to analyze in our calculation. We can't show it physically. We
See, we are getting a comment.
Yeah.
What you math. Okay, I suppose you are a student of class 8, but this is not a topic of class 8. This is a topic of quantum mechanics. Okay, it's a higher topic. You can read quantum mechanics in graduation if you do BSc in physics honors, or maybe higher topic. You want to know what is mathematics rational number of class 8 topic. We are not discussing it here. We are just discussing here the quantum mechanics thing. Okay? Now.
Okay, see here. We can only plot this term in the real world. We cannot plot this because this is imaginary, but it sticks there. It's always there. Why it happens, I will explain it in any other video. Here, see, this is a sine function. So here, the particle will be like this. Let me draw it well. Like this. This is a point of 0. The plot of this term is like this. It's sine function. See, put the value of x. X is equals to minus a by 2. Then you sine pi 2 pi x by a. Put x is this, 2 to cancel, A cancel, pi. It is 0. Put x is equals to plus a by 2. Then sine 2 pi x by a is again 0. This is C here. This will be the point of minus a by 4. And this will be the point of a by 4. Put x is equals to minus a by 4. And what we are getting? Sine 2 pi a by 4, keep minus by a, pi by 2, that is minus 1. And that's why the wave is at the negative max, plus a by 4 sine 2.
It's okay, don't worry. If you want to speak much English, it's not an issue. You can speak whatever language you are comfortable in. Yes,
See.
this is not a topic of class 8 rational number. This is a topic of quantum mechanics.
See this. Here x is equals to a by 4. So the function has max value. Its sine, this term can be plotted only here. We can plot only this term here, not this term. This is imaginary. And this is sine function. And at minus a by 4, it is minus 1. That's why here. And plus a by 4, it is 1 here. And at these two values, it is 0. That's why here. It's also the first excited state. Is it visible?
Yes.
First excited state, not the ground state. I will show you ground state in any other video. The particle is free, means it has no disturbance in between it. Within this region, the particle has no disturbance. That's why potential energy is 0 inside this region. Inside the region. And as we know, the particles inside this region, and extremely small particles, the subatomic particles, follow Schrödinger equation in non-relativistic quantum mechanics. And here speed is not very closer to the light, that's why you can use Schrödinger equation. See, so this matter wave function supports Schrödinger equation. Schrödinger equation. Okay, Schrödinger equation. First, see what is Schrödinger equation here.
Speak in between.
See, this is our Schrödinger equation from here. Minus s cross square by 2m. M is the mass of the particle. The particle which is moving in between this only, not beyond this, has mass m. Second order differentiation to this function, this, with respect to x, because it's a one-dimensional application of Schrödinger equation. When we go for 2 or 3-dimensional application of Schrödinger equation, in that case we have to use x squared plus y squared plus z squared plus v. This is the any disturbance within this region to the particle is this value. This is any disturbance, anything which is disturbing or supporting, which can affect the motion of the particle within this region is this value. But here the particle is free, so the value of v is 0. And to the right side of the equal to, we have I h cross d. This again function is differentiated with respect to time. See here, to the right side of equation, Schrödinger equation, differentiation of the matter wave function with respect to time. And here, second order derivative with respect to x. And v is 0, so this term will be 0, so we ignore this and we have this only. By putting the value of this here and doing differentiation to both the sides, we'll get the energy, total energy of the particle, free particle within this confined region in the first excited state. See here. After solving this, the value of this is, let me to solve this anywhere else. How many people are watching? Okay. See this. Let me find this term only. See this. D squared this by dx squared. Put the value of this, a sine 2 pi x by a e power minus I e t by h cross. Differentiated with respect to x, whatever will be a result, again differentiated with respect to x. See, this will be.
Thank you so much for being in our life.
A cos.
You are also a great student. Try to read better for your class and try to perform better.
If you have any problem in your class matter, you can ask us. If you have any problem, math, science, you can ask us, we'll solve your problem. See this. This sine 2 pi x by a, and then 2 pi by a x. D by dx. Again we have to differentiate it, and then 2 pi a by a comes out. This goes to this. So only this term has x, means only this will go under differentiation with respect to x, and it will remain constant. That will be sine 2 pi x by a, take here as minus 2 pi by a e power minus I e t by h cross. Clear?
Analyze it.
See, this means you have to differentiate the value of this function, this twice with respect to x. So first I differentiated this by putting the value of matter of function here. Only this term has x, it has no x, so this and this comes as a constant here and here. Only this sine 2 pi x by a goes under differentiation with respect to x. It will be, for sine it will be cos 2 pi x by a, and 2 pi by a comes here as a constant. Again there will be another differentiating term here, minus h cross squared by 2m. This 2 pi by a comes out, d by dx goes to this term, only this, and differentiation of cos will be minus sine 2 pi x by a, 2 pi by a comes out. This means after seeing whole this term, I can write here,
Wipe this part and write it. Here this is intelligent. Amazing.
See. See here. This. Finally,
Okay,
this we got
it's
this
okay.
term.
Navgan C40, the child has commented again. He is saying that I am going. Okay, you are going. You are waving us. You are doing bye bye. Okay, bye bye. Go and sleep. It has been too late. Good night. Take care of yourself and read. You are a class 8 student, so try to read better. And whatever problem arises, you can ask it on our channel. I will try to resolve your problems.
Is this visible?
I cannot see that there.
This
Yeah. Your finger is
here,
No, that's not good.
this.
Tilt your body slight so that the screen will be visible.
Let me write first. I need some more space here.
Tilt in this one.
See, just this term here. That will be, see, this minus and this minus becomes plus. So I'm not writing it again. I'm just writing the final term. What will be the final term here? That is 4, see, 2 into 2, pi into pi, a into a. That will be 4 pi squared by a squared. Then you have a. And then this and this. Sine 2 pi x by a and into t by h cross. And listen, this is exactly this. What do we have as a math wave function? This is exactly this. And that's why this term simplify in the form of this 4 pi square by a square, and this will be this. So after differentiating this twice and putting this value, we get this. That's the value of this whole LHS. Now I'm erasing this. I'm putting a whole this value to here in the equation. Is it safe here, this screen?
Almost no.
See. Solution of this. After solving this term, we get this.
Okay, you are being comedian now. See, this child, this student is telling you that thanks friend, happy life, you 101 years, okay. I wish you to live more than 101 years and thank you so much.
1,000 years.
Yeah, 1000.
I wish to live you 1,000 years. Your lifespan will be greater than a decade, not decade, century, but you will be over than 1,000 years, okay?
He's saying thank you.
Yes, very good. Study well and ask your doubts. See this. This term. How many are watching? 3. This LHS comes in. Now we have to go through the RHS. Again, we have to find the value of RHS and put it here. Let me erase this and I'll solve RHS and then put in the equation to get the value. See this. We have as RHS IH cross d psi by dt. IH cross d by dt. Put the value of this function. Again this function. a sine 2 pi
Okay, I got it. You are comedian.
x by a.
You are doing the comedy comments, laughing. Yeah, it's better. Enjoy life.
See,
Keep laughing.
see, the value of psi function is here. This is the matter wave function. This time, notice difference. Earlier, here, while solving for LHS, we have to differentiate this matter wave function with respect to x, with respect to distance, x, y, or z twice. But to the right side, we have to differentiate this with respect to time. With respect to time. That's why this term remains as constant and this goes under differentiation because it has t. It doesn't has t. I h cross, this comes as constant and this goes to this only. And for ease, I'm writing one more term here, c. Clear? The differentiation goes to this term only. I h cross a sine 2 pi x by a, and this e power minus I e t by h cross, and then we get minus I e by h cross. Notice it's an exponential term, and the differentiation of exponential term is whatever the term is that remain as the differentiation. This term remains as its differentiation, but we have to take care of the constant term with t. Here variable is t, and you have to differentiate with respect to t. So this whole term comes as usual, and the constant term I e by h cross comes here with minus. Now this minus I and I will become minus I squared. This h cross gets cancelled. And what we have now, e comes here, a sine 2 pi x by a e power minus I e t by h cross. And notice again, this is our function. This is the same function list. So substitute this value with this. And then we get here, minus I squared is minus 1, and another minus will become plus. So this becomes 1, e, and this. See, is it visible or not?
Yeah,
it's not visible. See this. After solving RHS, right hand side term, we got this, and this E is the total energy of the pre-particle which is oscillating or moving from here to here, not to that side, to this side. And this is the matter wave function. Put this value here. And what are you noticing? The function gets cancelled to both the sides. And the value of total energy is, means here, for 4 I can write 2 square pi square h cross square by 2ma square. That's the total energy of the particle, the free part. The particle is free. Remember one thing, the particle is free. Free means it has no disturbance in between that confined region. It cannot go to that side, to this side. Means it will never come out through this region, beyond this side and beyond this. Because in this condition, it's 0. But within this confined region, it has some function. Means it exists here in terms of sine wave with some imaginary time component. And this will be the energy of the particle here.
Tell them about the timing effect.
I will discuss it at then, don't worry.
Just a little bit.
This is the energy, total energy of the particle. The particle which is oscillating from here to here, and it's free. It has this energy. Okay? And this is not the ground state, not the minimum energy of the particle in this confined region. This is the first excited state. First excited state means it's not the least energy, not the minimum energy, just slight, the first value after the minimum. What could be after the minimum? this particle inside this confined region, when there is no disturbance, has minimum energy less than this. This is just energy higher than the minimum energy. And it gives you a formula. N square h cross square pi square by 2ma square. Okay. For minimum energy, we should take n equals to 1. For first excited state, we should take n is equals to 2. And this is second state, n equals to 2. Means that is the first excited state. I have discussed about the ground state energy in one of my videos, and I'll upload it in 1 or 2 days. The first excited state will look like as this. The same particle will be in first excited in ground state when n equals to 1. The minimum energy, the least energy is in this shape. But in the first excited means just first possible energy after minimum will be like this. That is sine function, this is the cos function. You can watch my video. I will upload it in 1 or 2 days. Clear? Now one thing here. See, the function is 0 when x is smaller than minus a by 2. Means when to left of this region, there is no probability of finding particle. Means particle will never exist there. And to this particle will never exist there. But this is not true in quantum mechanics. It has some of the possibility to be found in this region and to get found in this region. Why? Classically, you can say that the particle is always confined, always exists in this confined region. It cannot go beyond this and this. But in quantum mechanics, there is some possibility. It will be like that. Suppose you have been locked in a room with very strong concrete wall and ceiling and floor, everything. The gate is locked. Means there is no room for you to escape from that room. That is the classical reason. And that a particle in this region is exactly like the classical. But do you know there is some probability of you finding outside the room in quantum mechanics? Quantum mechanics tells us that a particle can have some probability. It could be possible that the particle will get out of this boundary, out of this forbidden region. Like in the room, if you are in a very concrete tight room or very strong wall room, there is no any hope for you that to get out of this room. But you know, in quantum mechanics, there is some hope. If you are knocking continuously to the walls, then you might find yourself outside the wall. That is the quantum tunneling. And I will explain this in any other day. So, understood? In first excited state, the particle is going like this. Means it has motion along sine wave. In ground state, it has motion along cos wave. Clear? That's for today, this live. If you have any doubts, any suggestion, or if you did not understand any particular step, then you can ask me in comment. And for detailed video and for other videos related to this, you can watch my channel Physics and Universe. And thanks for the watching. That's the end for this live.
And
thanks for you all who have been in live since beginning to end. And
there is one child of class 8.
Yes.
@navgun C40. This is the name of the channel. And
oh, you can comment your name. I think it's not your real name. You can comment your real name.
It's the channel's name.
Channel's name, I know. And it's glad to know that you are in this live. You have been in this live since beginning to end.
Yes.
And that's very good. Thanks for the watching. And study well. Ask your doubts, okay? And what's the other one? No, any other comments?
No.
Okay, that's it. So that will be end.
Good night.
Have a good day. Good night. Now see you in later.
Thanks for watching.
Thanks for watching. I have said trivial time.
Industry.